Hi, I'm Tally Motes, and today I will be discussing Lab 5 of Physics 2212, titled Faraday's Law. The goal of this lab was to collect observational data of a falling magnet through a conductive tube. My experimental time for the magnet to fall through was 1.2 seconds, and the computational time was 0.669 seconds. Many physics principles were used in this lab. We first had to imagine the tube as many different rings. We used Faraday's law to calculate the magnetic flux during the experiment and to find the current in each of the rings. We used Biot-Savart law to calculate the force exerted on each of the rings due to the magnet. We used Newton's third law to calculate the force exerted on the falling magnet by the whole tube of current-carrying rings. And finally, we used Newton's second law in the computation and model for position and velocity. For the physical experiment, I dropped the bar magnet down the aluminum tube 5 times. I used foil instead of a ferrous tube because it is not magnetic. This way, the magnet could fall completely through the tube. I recorded the time it took to drop for each trial. The result of each trial is seen here. The average fall time was 1.2 seconds. The measurements I used in my code are seen here, including the results from my physical experiment, which at the end I will compare to my computational model's results. Here you can see some of the most important parts of my code. First, I set up my initial condition. Next, I calculated the magnetic field at a position r relative to the bar magnet. Then I calculated the rate of change in the magnetic flux through each of the rings. For the fourth step, I used Faraday's law to calculate the current induced in each ring by the falling magnet. Next, I used the Biot-Savart law to calculate the force exerted on each current-carrying ring by the falling magnet. After, I used Newton's third law to calculate the force exerted on the falling magnet by the whole tube of current-carrying rings. Then I calculated the net force on the magnet by including gravity. Finally, I used Newton's second law to write position and velocity updating code to model the motion of the falling magnet. In my code, the black cylinder is the tube. The magnet is falling downwards, so the increasing change in flux also points downwards. Therefore, there is an induced current in the counterclockwise direction. In the simulation, you can see that the induced current is blue, so red is clockwise and blue is counterclockwise. It depends on the orientation of the magnet for which is which. The code says the North Pole goes first / below the South Pole, which is why we get the results that we do. In this experiment, if we were to flip the magnet around, there would be no difference in dynamics. For my physical experiment, I got that the average time for the magnet to fall all the way through the tube was 1.2 seconds. The time in the computer simulation was 0.669 seconds. We could make the computer simulation more accurate if we split the tube into more rings and analyze the system at more points. The biggest thing that hurts the accuracy of the simulation is that we treat the tube as a dipole and not a cylinder. Here you can see the graph produced by my computational model. In my model, the velocity drops steeply and then plateaus. When you think about the way the forces are added up at each small ring, it makes sense that the net force acting on the bar magnet due to the tube is increasing with time, thus slowing the magnet down over the course of its fall. To conclude this lab, I looked at 2 different questions. The first question was, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The answer is that with decreased resistance, the induced currents would be larger. Therefore, the magnet would fall slower. This relationship can be explained using Ohm's law. If the resistivity went to 0, the velocity would go to 0 and the magnet would hover. The second question was, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? The answer is that removing parts of the tube would decrease the number of rings, which would in turn decrease the magnetic force. This would cause a decrease in magnetic fields, and the magnet would fall faster.